The concept is how to build worlds, rocky ones, which obviously, like the Earth, might have an iron nickel core, a silicate mantle, and then some kind of exterior crust. And on Earth, of course, we have a watery surface too. Um, so it's a complex and really challenging problem to understand how we go from the beginnings of a solar system, our protoplanetary disks, with dust, gas, and ice, to planetary bodies. So we need to stick things together in some fashion. Some of the oldest solids in the solar system are thought to have condensed around 4.68 billion years ago. That's billion in the US sense again, 1,000 million. So we're going from these primitive bodies which are unmelted and more or less what we would consider in geology as conglomerates, so bringing different things together. Then, of course, they get large enough. Aluminium begins to decay radiogenically, gives off heat. We've also got energy from the impacts of these things coming together. They will then differentiate, so we have that core, that mantle, and that exterior crust, as schematically illustrated there in terms of differentiated bodies. And ultimately, these grow to planet size, and we might end up with something like the Earth-Moon system. But how do we go from the start there to having a body that might be habitable? This is the long-term consideration of how we get to life being able to evolve. So we're going to focus on this stage, beginning of how we build worlds. We are going to look at the chemistry as a means of deciphering that. We can classify elements in terms of how they behave in relation to a geologic system. So lithophile there means that the elements like silicates in a rock. Siderophile means that they have an affinity for the metal. Chalcophile means that they like the sulfides. So I often look at siderophile and chalcophile elements in my work. And atmophile, of course, means that those elements have a tendency to be in the atmosphere. Elements can be classified in different ways. So some of you may be familiar with the astrobiology classification, but also there is the cosmochemical classification there, just shown for reference. And just to remind you, of course, that the cosmochemical classification scheme, which deals with how refractory an element is, so it's temperature related, is a broad description that might be relevant under a range of conditions, whereas the Goldschmidt classification scheme is really quite Earth-centric again. So we have to keep that in mind when we're dealing with planetary materials. So this diagram is probably quite complicated unless you've seen it before. So if you were to plot the estimated bulk composition for each element in a given planetary body, here with Earth as a reference, you can show a broad slope on the right-hand side of the image, which may indicate some degree of loss of volatile and moderately volatile elements, so those at lower condensation temperatures. The angle of that slope may vary between bodies, so as you can see, Mars has a gentler slope there, and the APB, as it's referred to, is the angrite parent body. We will get to angrites later, but those are rocks that formed over 4.5 billion years ago, so they're very old, and they're also rocks that are melts in some form from a planetary precursor, so a protoplanet perhaps. And I've circled there a set of elements toward the bottom, which are refractory. They are the highly siderophile elements. Platinum is one of them, so you might also refer to some of these as the platinum group elements. And we'll look at how important they are in tracking the processes of planet formation. Why are these particular tools really useful to us? What can we learn by looking at rocks from space? All sorts of things. So we can obviously use ion microprobe technologies. This is Nicola Mari's PhD work, where he looked at the sulfur isotope composition of individual sulfides, so individual minerals within the Narcolite meteorites, which are a set of meteorites from Mars. And so using those meteorites, we were able to look at the surface processes on a planetary body, in this case Mars, looking at the extraterrestrial volcanic edifices, and then looking obviously at the interactions, so what we can capture of surface and atmospheric compositions by deciphering the message in the chemistry of the rocks. Here we're going to focus on ancient rocks, so those that formed over 4.5 billion years ago that really capture that early stage of planet formation. They are hopefully the key by looking at sensitive geochemical traces to address particular challenges, so particular aspects of how those planets come together and how they grow. What happens during that growth? When do we add volatiles? Can we infer that with confidence? So the rationale behind using highly cytophile elements in particular is that when we have a body that's been differentiated, so with a metal core, silicate mantle, and a silicate crust, we can hopefully, if we have the expertise, look at the abundances of elements such as osmium, iridium, platinum, palladium, ruthenium, rhodium, and rhenium, which are the highly cytophile elements, and as such love iron. What happens is that we think that they have very high metal silicate partition coefficients. So obviously not all of you will like the subject area, but in excess of 10 to the power of 4, which means in effect that they will be entirely stripped from that silicate mantle to concentration levels which are below our ability to detect them. So we won't measure them in the silicate mantle or the melt rocks that are derived from that. They will instead reside entirely in the core of that body, if that is the only process that we are seeing. So if we only see core formation, we would not expect to measure highly cytophile elements in the resultant mantle and melts. And importantly, we can then compare our highly cytophile element abundances, their relative proportions to chondrites. Chondrites have quite a lot of these elements, so if we are seeing any late impacts, then we'll be able to tease out that signal. The reason why we can do that is if you think of it like a dye in water, is that if you're adding in a small amount of something which is highly concentrated, then hopefully you'll be able to see what level of concentration you have that at. As you can see, we can in fact measure the abundances of highly cytophile elements in our rocks from Earth, and also those from Mars, the Moon, and elsewhere. This is early work by Paul Warren, so this is in the 90s. And you can also see a broad trend in relation to magnesium oxides. This is in a bulk rock. We often use magnesium oxide as a proxy for understanding how melt processes operate in silicate rocks. So at high MgO, we're in a mantle environment, we're in that starting material, and as that rock melts and crystallizes and evolves, we'll have lower magnesium oxide. So if we have a broad trend such as this, we can backtrack to where the star is. That star at the top left-hand corner will essentially tell us what the absolute abundance of that highly cytophile element is in the mantle of that body. Understanding planet formation and the evolution of the solar system is something that we have to do in partnership with other disciplines. We need to bring a lot of information together. So there has been a paper that's relatively recent in Nature Astronomy. So here we've got an integration of astrophysics, the dynamical modelling of the solar system, resting on highly cytophile element data as an underpinning reference point. We can also, there are papers which refer to the highly cytophile elements as being a clock, which we can use for understanding solar system history. So if our data is robust and correct, that's really important. If, however, it's flawed, then we've got to be cautious. But one of the conclusions that was drawn from this work is that the asteroid belt was either never significantly more massive than today, or it was rapidly lost most of its mass early in solar system history. So this is obviously a really important point for understanding what has happened to our solar system over time. And that whole context obviously frames why the Earth has evolved in the way it has, and shapes, why we have life here. There are a number of other papers which make quite a splash, So they talk about what we call accretion. So accretion is the addition of material to a silicate body after the core has formed. So it's that ongoing delivery of material. So if we were thinking about panspermia, for example, tracking this process might be important. We want to know how much is added. So again, we're trying to decipher the level of dye in our other material. There's actually leverages some older data from diogenites alongside some new data for highly cytophile element concentrations in eukaryotes. And what you can see here is that there is a broad trend. So this is another way of calculating the absolute abundance of a given highly cytophile element in the mantle of that body. So again, we're assuming that that fractionation that we see is the result of a magmatic process, a melt process. We look at the ratio. In the example given here, we're looking at rhenium versus osmium. And as we track it down towards the line going across, that line going across gives us the chondritic reference. So if we, so this is a bit of circular reasoning, if we have a chondritic relative abundance in the mantle, the point of intersection will tell us what that level of concentration is. And then we can, there are various ways of then testing that to make sure that we have self-consistent data. But having worked out what the concentration level is, the level of dye in that material, we can then do some calculations to unravel how that relates to the mass percentage of the body. And the overall picture from current knowledge, if we accept the data in the form that we have it, is that larger bodies such as Earth and Mars have a greater proportion of accretive material added to their mantles after core formation than smaller bodies such as the Moon and Vesta. So in terms of gravitational attraction, that might be broadly what you expect. So if that data is correct, then it's really important for informing models of solar system evolution. So it feeds into what we understand from other aspects of geochemistry, some of which I think Paul will speak to, in terms of the movement and mixing of materials over time, the role that Jupiter has played, has it always been in its position? If it moved, how much did it move? And what were the consequences of that? If we take a set of meteorites called diogenites, there are many of them. I'm showing you one example here. They actually relate to the 4 Vesta asteroid, which was the subject of NASA's Dawn mission. As a consequence of that mission, there's spectral data for the surface, so we have an understanding of the composition on the surface. And our meteorites, in being linked to them, give us a ground truth of the processes operating on 4 Vesta. If we look at the triple oxygen isotope ratio, so 16, 17, and 18 oxygen, we can group our meteorites. And so here, I'm just giving you an indication how we use this system. The HEDs, for example, are shown on the diagram on the left. That fractionation line tells you that they come from the same body, and it's distinct from the terrestrial fractionation line for the Earth and the Moon. So they're not from the Earth and the Moon, they're from somewhere else. And they all are from the same place, we think, broadly. We know that they're ancient. We know that they're composed of olivine and orthopyroxene minerals predominantly. There are other minor phases. We also know from their composition that they were probably produced under conditions that are relatively low in terms of FeO, so relatively reduced conditions for melting. And we could take a series of diogenites to look at. And their meteorite names or code names are shown there. NWA stands for Northwest Africa, so that means that that was where that meteorite was found and brought back. All of these meteorites that are listed there are finds. Falls are really exciting, so if we haven't observed fall, we can go and collect that meteorite without it sitting on the surface for a long time. What we can do to analyse the highly cytophile elements, because they are refractory, they're not easy to get out of the rock. So we have to take our rock or our mineral phases and digest them in acid. So inverse aqua regia in particular, at high pressure and high temperature. So we have a confining pressure from the gas that's put into our digestion chamber, and then we heat that up and leave that cooking overnight. We then have subsequent processing steps once we've liberated the highly cytophile elements and got them in solution. So we're working in a no metal clean lab. In terms of making measurements for the highly precise osmium isotope composition, which is a result of radiogenic decay, so 187 rhenium goes by beta decay to 187 osmium over a long time period. We'll measure that on a thermal ionization mass spectrometer. So I just wanted to show you the fancy instrument. The sample we've chosen, it sits right in the middle of a set of results from a previous publication, as you can see here. Now, those data generally show a broadly flat pattern on this plot in the top right-hand corner. That really indicates that the previous work showed that diogenites have chondrite relative abundances of highly cyclophile elements, and that the absolute abundance of those elements within any given diogenite varies over several orders of magnitude when they're all compared. By looking at the slices of section of the diogenites, it's been inferred that the breccia zones within them are free of highly cyclophile element-bearing sulfides and metals, and that probably those highly cyclophile elements might be hosted within inclusions within the silicates, but those inclusions in themselves have a range of nickel and iron, for example, in the metal. So there are different ways of interpreting that. So it's a broad indication of whether we have a chondrite contamination or not in the sample. At the moment, it's been inferred that we don't see that, but it's a non-unique interpretation. So we want to test the theory that diogenites are giving us a pristine signal of what's happening on the 4 Vesta asteroid, that sampling its mantle directly, and that's not disturbed. But is that true? So if we take a look at Northwest Africa 5480, you can see that there's sort of textural complexity within that sample. There have been previous studies that have inferred that the sample has textures within the individual grains that are analogous to shear in the mantle, but again, I think we can disagree over exactly what processes are required to produce that shear in those samples. And by looking at individual parts of the sample, we can see that there is variation within the individual sample in terms of the abundances of the highly cyclophile elements, but also they fractionate relative to one another. And these results are slightly different to the earlier study, which is shown in the dark grey bar across there. If we look at the isotopic composition, which gives us a time resolved kind of signal, it's quite, it's very sensitive to process. We can see that we have a bunch of samples which are plotting at a point that intersects with the chondritic range that's known in our solar system. And we also have samples that are plotting to higher 187, 188 osmium, and so that's indicative of those having sort of radiogenic values, so higher rhenium osmium, and that high rhenium osmium has been integrated over time. So the findings from our study, sorry to go back to the model. So we've seen a broad mixing relationship. So what does that broad mixing tell us? Do we have a robust signature on the signature side, actually what we're seeing for the Vesta body, in which case it's very different to previous work. So perhaps diogenites do not provide a direct record of the Vesta mantle HSE composition. In consequence, the models that rest on them will need to be revised. So this is the astrophysics and dynamical modelling of the solar system. To break the samples down in this way, to look at individual parts of them, you're dealing with relatively low levels in the lab, so it's quite challenging. You need to have low blanks, and you need to have a lot of patience on the instrument. But doing that work is worthwhile because it opens many doors for future research. So we can look at, accretion processes on a planetary body, we can look at giant impact scenarios, and we can feed all that information into what we understand of solar system history. There's a student project that's starting up shortly, so I want you to keep an eye out for Jordan Young. He's going to be revisiting the Anglite meteorite group. There are a number of new samples, which I will hope to get my hands on to help him. And the Anglites in themselves, these are, I should say, these are backscattered images, so they're giving you an impression of the different minerals within them. Geologists really love to look at their minerals in their rocks. And Anglites are beautiful, they're very fresh meteorites, so even though they're very ancient and they're melted, they are, they haven't experienced a lot of alteration on the surface of the Earth, and they don't seem to have experienced a lot of alteration on the parent body from which they come. So the information they hold is hopefully very robust for the purposes of what we want to look at. They do have different textual groups, so Jordan will be looking at various ones of those. I'm going to invite you to Edinburgh, so don't want to say too much about that. There is the early bird deadline has passed. The late deadline, though, is the 21st of October, and I'm still receiving abstracts this morning. So you're very welcome to participate in that meeting, which has themes that are common with, I think, the North Cells network's objectives in this meeting. And then somebody asked about databases. For if you wish to dabble around in what meteorite compositions are, there are some databases where you can start doing that. So,